Hello and happy Friday to you all. Today, you're going to take a little bit of a reminder look at interference of waves. This is only a little bit new. Actually, it's not really new because we've looked at this diagram before, but it leads us into talking about something called diffraction. That's something that all waves do. And specifically, that's going to lead us to talk about single slit diffraction. This is what happens when a wave passes through a very narrow gap, and it actually ends up producing an interference pattern. So the diffraction and interference go hand in hand in that system. The third of 3 sets of problems have been posted to Schoology. Next Monday's quiz was originally scheduled to be closed note, is going to be an open notes quiz. Don't forget to work on the labs you've already done, submit them, get those practice problems in. Now is an easy time of year to get lazy and get behind. You got 29 school days left. You can do it. Don't be the person who gives up with half mile left in a marathon. So Monday, got that open note quiz. Tuesday will be the lab we were originally scheduled to do today. Wednesday, this lab was scheduled for Wednesday, and then Friday is wrapping up light and optics. First thing first, diffraction. This is what diffraction is. It's when a wave encounters a narrow gap, or it could even be a little pinhole, and it spreads out. So you'll want to make sure you understand that's the underlying idea behind diffraction. Here you can see some water waves that are passing by the edges of islands, and you can see that the waves bend around the edges of the island. Don't draw this diagram yet. I have something for you a little bit better. But this is the basic gist, is you have a whole bunch of waves that are what we call plane waves. That would be like waves coming in from the ocean. And they bend around each corner of a gap. So this is an okay. Hi there, someone just came in to check on me, so I had to pause. So again, this is a decent model of diffraction, but it leaves a little something out. This is why I didn't want you to draw this diagram. So it only shows the spreading around of each corner. So this is showing it spreading out over a 180-degree arc. It really spreads out over 180 degrees from each edge, and this shows it only bending 90 degrees. And here's what I mean. So this diagram only shows the wave on the right side gap spreading 90 degrees, left side gap 90 degrees. This next diagram is what to sketch. It's not hard. So you have a narrow gap, and you show some straight lines coming in representing a plane wave. This is how a lot of waves come at us. Sound waves, unless we're standing right next to a sound source, they pretty much come in as plane waves. And you want to show that around each of the edges of that barrier, it spreads out into a circular path. And that means that you have one set of waves spreading out from the left and the right, second set of waves from the right, and they interfere in the middle. That's where the lines cross. That's the only place we can really talk about the interference, where you have the two waves meeting. If we go far to the right or the left, that's only showing one wave, and that's not a place where we would encounter interference. So if you need a little more time to sketch this, you can hit pause. But moving on to the interference of light. A reminder that light is an electromagnetic wave. That is something you should already have in your notes. So think about what it looks like when light waves interfere constructively, and think about what sound waves sound like. If you have two waves interfere constructively, like when you wandered around the room listening for loud and quiet spots, the constructive interference spots were loud. Well, the equivalent of loud in light is bright. So then what would it look like if you have a couple of light waves that are interfering destructively? It's going to be the reverse. It's going to get darker, it's going to get dimmer. There's the potential that it completely gets dark. So I've got a few diagrams to show you, and then I have one slide that has kind of a summary of the diagrams that would be good to jot down. So right now you're just looking at this, and you are taking your best educated guess at which of these two patterns would show two waves that interfere constructively. So in the top, the two waves have their crests and their troughs occurring at the same spot. In the bottom, the two waves have their crests meeting the other one's trough, and vice versa. You guessed it, the top one is going to show constructive interference because they're going to build on each other. The bottom one, they're going to diminish each other a little bit. The shallow trough from one is going to decrease the amplitude of the taller crest on that orange line. So there's our constructive. Well, we already went through this. We said which one was the destructive. That's where crests and troughs meet. But then take it out a little bit further to think about what it would look like if you had two waves that interfered completely destructively, 100%. So just like in the destructive interference pattern that was shown, you would have a wave. You would have crest, trough, but you would have the opposite part of the wave meet from that second wave. So it's always crest to trough, and what makes it 100% is that their amplitudes are the same. So here are the sketches that would show this. So constructive, that's what that looks like. Maybe you choose to draw that diagram on the right, really the one on the left that is what's important. Partial destructive, again, the right side diagram with the green dots kind of shows the result of it. What's really important is to show the two waves on the left. And then 100% destructive would be, as you saw, the two waves matching crest to trough with equal amplitudes. And if you need more time to sketch it, just hit pause. So now we're going to put it together for and talk about diffraction and interference of light. That's going to lead us to this phenomenon we call single slit diffraction. So back to this. We saw this diagram just a few minutes ago because we want to reiterate when a wave passes an edge of something, it spreads out over 100 degrees or 180 degrees. What's the difference, right? Like a pebble dropped in a pond when there's a wall behind it. Well, the pattern that would show up on a wall, if you were sending like a single color, like a laser through that, it would look like that. That wide spot in the middle we call the central maximum, and we're going to talk about that amongst a few other things. So this is our last topic for the day. This is going to be what we are investigating in next Wednesday's lab. So you want to jot this down. This is how we do some calculations with where we see destructive interference when you have a single color of light from a laser pass through a very narrow gap. So right now you're just writing down the equation, and there's a diagram that goes along with it. So you know what sine is. It's a trig function. And m, we don't know what m is yet, but you'll find out. That funny looking upside down y, that's lambda. That is the wavelength. As it turns out, a is the width of that very narrow gap, that slit. M is what we call order number. We're just going to leave that be for a second. A picture helps. So it's going to be which dark spot you see. The first dark spot is m equals 1. Second dark spot is m equals 2, and so forth. We will talk a little bit about what happens when you send light through two very closely spaced, very narrow gaps, and that's actually part of Wednesday's lab as well, but that is not for today. All right, so really the last thing for the day that you need to jot down, and then I've got just a couple pictures to show you, is a diagram that kind of makes this all come together. So what you want to draw is on the left side, that's just where we have our very narrow gap. Remember, A is the width of that gap. The right side, that big gray thing, that's just where whatever we're throwing the light onto. It could be a wall, could be the front whiteboard, could be whatever. And we have this reference line, that dashed line that goes right down the middle. So we measure with respect to that. And what we're going to be dealing with these gaps, that A value, they are going to be tiny, very, very narrow, like the width of a paperclip. And I mean of the metal of the paperclip. So not even a millimeter. So that's going to be a very, very small gap. So we're going to see a dark spot along that path, and that will form an angle. So we'll have that black dashed line that represents the middle of this pattern we're going to see. And then there will be a dark spot where that blue, thicker dashed line meets. I would say don't bother drawing in this wave right here, but it's just showing where you're going to get a lot of amplitude, so bright, and it's going to show where you get not much. So don't bother with that part, that kind of wave looking thing. And then hold off on these labels, the Y2, Y1, O, that's right down the middle, and negative Y1 and negative Y2. Hold off on labeling those for just a moment. And then a meaningful value is the distance between this spot where we have a gap and where we are throwing the light onto a wall. All right, so now you're going to fill in this actual pattern you see. So just draw some ovals that look roughly like that. So we'll get rid of that. That wider central oval we call the central maximum, and in between the ovals it is dark. So this is where we label Y1, Y2, negative Y1, negative Y2, and that's where we get to this order number, M. So if we are looking right down the middle of this pattern, we see a wide bright spot, and directly to the left or the right, well, in this case, directly above and below it, that's what we call the first order. That's the first dark spot. The second set of dark spots out are m equals 2. And I bet you can figure out the pattern right there. And hit pause if you need to. So think about that angle that's indicated. We're going to call that angle dark. That's the angle that the dark spot goes along. And we have it at m equals 1. So we know the distance between the narrow gap and the wall, and we're going to make this pattern as big as possible by using a really big length. And y1, that is literally a distance. Y1 is the distance from that center dashed line O to the first dark spot. So you get out a ruler, you measure that. You get out a ruler, you measure the distance, L, from the narrow slit to the wall, and then you can figure out the angle. And that's just going to be some trigonometry. Inverse tangent of opposite over adjacent. So that central maximum, this is something that's going to come up mostly in lab. It's actually easier to measure the width of the central maximum and divide by 2. That gives us y1, but that's just a practical matter for the lab. If you need more time, hit pause. So this is just showing a single gap and the fact that you get this very regular interference pattern from the wave, the light that spreads out from each edge of the gap. This is what the pattern will look like on the wall. We're going to be using green lasers, but we might pull out the red lasers too. We'll see when it gets to lab time. So this shows both a green and a red for the same width gap. Turns out the color of the laser makes a difference. Green doesn't spread out as much as red. Blue spreads out even less than green. So that's labeled right on there. The first order minimum just means dark spot. So that would be m equals 1. The second order minimum, it's the second dark spot out. That's m equals 2. And this is just showing what happens when we narrow the width of the gap. The top one, it's only 0.16 millimeters, and by the bottom, we're down to 0.02 of a millimeter, and it really spreads the pattern out. So again, that's what we call the central maximum. Almost there. We're almost done. So the little animation on the left is showing this pattern as waves come in, just puts a little motion to it. On the right, it's showing what happens if we decrease the distance between the edges, so we narrow the gap. Got a slightly bigger version of that, and that's the last thing I'm going to show you. So S1 and S2, those just represent the edges of the gap. So we bring them in closer, 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 and we can see that that pattern starts to really spread out. There isn't, you don't see as many lines crossing when they get close. When they're far away, you see a lot of cross-hatching. So you're going to see a lot of dark, bright spots in a small gap. Okay, that is it for the day. Have a good weekend.